Good afternoon, everybody. We are today presenting mission-critical AI for space and aerospace applications. My name is Dave Ojika from Flapmax, which is a company that is building UAVs and CubeSats. I'm joined by Shreya.
I am Shreya Mehrotra from Altera, and I lead the embedded strategy and messaging for our IP tools and software for Altera FPGAs.
Okay, so to start off, I really love this quote by the RISC-V International Foundation, which is that the era of a traditional one-size-fits-all processor model is over. And this is really true because if you were at the OCP Summit just last week, you would actually see the number of vendors that have made numerous announcements on how they're integrating their processors together. For example, if you look at Tenstorrent, which is kind of, they needed the R&D acceleration around ASIC and analog, and just kind of going up that stack all the way to the full stack, rack scale, data center wide deployments. We know OpenAI also announced with Broadcom not too long ago as well. So we believe that this trend will continue to increase over time, where vendors are very tightly coupling their processors together. And that what will be key is the orchestration between these cores over time. And we think that this evolution will continue to actually increase over time, specifically for mission-critical applications. So whether that is space, aerospace, CubeSats, UAVs, it is just not enough to focus alone on raw flops. We believe that orchestration and the data movement and workflow between these cores would play much more significant role over time. And so in the rest of this presentation, we'll be sharing some of our learning insights on how we're building two platforms. As I mentioned earlier, the FlapZero CubeSat and the SkyZero UAV platform, both powered by the Altera platforms, Agilex. So just to paint a picture of what that looks like, the first one, the CubeSat, is essentially 4 FPGAs connected in a pipeline approach. So that's really very simple. Data in, it flows through the pipe, data out at the end. The second one on the right is more of a graph-like architecture. So this is more it's more graph-centric. So it's a lot more communication going on. And so this really mentions the fact also that I mentioned earlier, that is communication is really very important. We all know how AI is starting to disrupt workforce today. We at Flapmax believe in the idea of helping to train the next generation of scientists and researchers. And that's why for the first platform, FlapZero, we are already engaging with universities, K through 12 students, to help to train them to become the next gen scientists and researchers. So the first platform, FlapZero, is powered by an Agilex FPGA from Altera. It has a RISC-V integrated control processor, it's a softcore, which Shreya is going to talk about in the next few slides. And it's designed for classrooms to space missions. We will be releasing the dev kits next year. In 2028, we'll be sending one of these boards to space. There's a QR code you can scan to stay in the loop on how we are developing this over time. The second use case is the UAV platform. On the right is one of our interns. Next to her is Altera CEO at the recently completed Altera Innovation Summit. So she did a wonderful job presenting on the platform that she built while interning with us. Two key takeaways from her work is the fact that we're able to accelerate node-to-node communication between these FPGAs by up to 10x, while achieving up to 2x in terms of LLM compute speed up. So in the rest of this next slides, I will hand it over to Shreya to talk about how we're leveraging some very interesting announcements that they made for our work.
So I wanted to talk a little bit about our NIOS V solution. For those of you who are not familiar with it, it is our RISC-V IP that we have for our Altera FPGAs. We took the RISC-V instruction set architecture that is an industry standard, and we've adapted it for our FPGA devices at Altera, because we wanted to give our existing FPGA customers the benefit of the RISC-V ecosystem. This is a softcore processor inside of our FPGAs. The most common use case for a soft processor is really control. Most of the embedded applications use NIOS as a microcontroller or some sort of control mechanism. And so that makes it a perfect fit for what Flapmax is doing for their RISC-V application. We offer it in 3 flavors, C, M, and G. C is if you don't care about performance and you just need a super small footprint, we have the compact microcontroller. Then we have the M core, which is balanced for size and performance. And then there's the highest performance core, which is more featureful, which is the general purpose processor. Similarly, on the tooling side, we've adapted it for our development tools, Quartus, which is our FPGA development tool. And then we also have the latest Visual Designer Studio, which was introduced in our latest release of Quartus. So we've adapted this IP for our existing development flows to make it really easy for customers to be able to integrate this RISC-V IP into their development flows and deploy in their end applications. I will talk a little bit more about Visual Designer Studio, but it is our next generation system integration tool, which is really intended to make design entry intuitive. And the embedded development tools coupled with the hardware abstraction layer that we offer, as well as components from the ecosystem like third-party RTOSs, all of this is intended to provide a full-fledged embedded solution for our customers. So Dave talked about Sky0 and Flap0. And if you remember, one of them was a serial topology with multiple nodes, and then one of them was mesh. So each of those nodes, you can think of them as FPGAs. And I wanted to kind of show you what is being implemented in each of those nodes. So this is the system, a NIOS V system, where NIOS processor is doing all the control and orchestration for this application. It is integrated with other IP in the system, like there's some on-chip memory, external memory, depending on which device you're using, Agilex 5 or Agilex 3 platform. There's some custom logic, like AI or DSP blocks that can be stitched into the design, and then something for communication, like a hardened I/O subsystem, can be Ethernet, PCIe transceivers. So on the hardware flow, we use all of the Quartus tools and the integrated development tools to put together the IP, make the connections, do the address assignments, and then we generate the HDL and compile the design and generate a bit stream for the FPGA. And then it involves generating the handoff files that talk between the hardware and the software world, so that's the board support package. And then similarly on the software side, we generate and build the application that goes on this NIOS V, the RISC-V CPU on this FPGA platform. So here I talked about what we're building, and on the next slide here, kind of wanted to show you a little bit of a quick demo, a few seconds, just a sneak peek into how we're building it. So this is the Visual Designer Studio environment. It is really to make design entry intuitive, faster, reduce the time to put together a design from days to hours. It is as easy as you can just drag and drop the IP onto your canvas. So in this case, I'm going to take a NIOS V M processor. I'm just going to plop it onto my canvas. And you can either use the default settings, or you can change the configuration and instantiate it. There's things like smart connectivity, so it suggests connections between IP that you can then just click or make multiple connections. We also have automatic address assignment. And then there's things that are not covered here because I just wanted to give you a quick sneak peek demo of this. But there's things like tickle scripting. Every action is tickleable. There's hierarchies you can navigate through. You can import custom RTL and logic into this. But on the hardware side, this would be part of the development workflow. And then you would generate your HDL. And then finally, stitch it with the rest of the logic if you have any top-level logic inside of the Quartus tools. And then the next is, then you generate the BSP, and then the next is the software development flow. So our official solution for software development and debug is the RISC-free IDE, which supports the Eclipse environment as well as Visual Studio Code. So depending on what developers are familiar with or they prefer or comfortable with, you can use any of those environments. And of course, we're also trying to work with more partners, vendors from the ecosystem to adapt and support more tools for our IP and operating systems as well. So the key takeaway that I want to drive home here with this slide is that the RISC-V IP coupled with our development tools, hardware, software, and then components from the ecosystem like third-party RTOSs, compilers. With all of that, the goal here is really to scale ease of use and make it really easy for customers like you, like Flapmax here, to be able to easily design, deploy, build their solutions quickly, smartly, easily, successfully.
So Shreya talked about how we are leveraging VDS, Visual Design Studio. What's interesting is it actually makes it very easy for us to kind of scale the architecture to hybrid architectures. So in this case, we have Flap and Sky. That is the hybrid architecture pipeline connected to graphical architecture. As I mentioned earlier, the key challenge is not so much the compute, but really how you orchestrate your data, your workload across these compute nodes. And so we're introducing RISC-Bench, which is a benchmark for heterogeneous AI. It separates compute from control plane while defining a new efficiency metric, which we call SIT, as shown in this diagram here. And on top of all that, it leverages RISC-V as the orchestration layer. To make this easy for developers to build, deploy, and test in their own platforms, we've kind of decoupled this into 4 key kernels. The first one is streaming to memory streaming, that is DRAM to SRAM. The second is streaming communication latency, that is the latency between chip-to-chip data movement. And if it's a single platform or a single chip, then it's the data input through the IOs and data output through the IOs. Aggregate throughput is the combined throughput of the various cores for that particular platform. And the sustained throughput is really the flagship metric that we're introducing. So when you combine the sustained throughput at those peaks that you see over time, you come at the sustained instantaneous throughput metric. So we've ported RISC-Bench on TensorRent. Even though we started with the FPGA platform, we're able to very easily port this into a heterogeneous computing platform like TensorRent. We could as well connect the FPGA to TensorRent and look at that as a single heterogeneous platform. But TensorRent is heterogeneous enough because it has already RISC cores on there. It has the AI processors. So if we zoom out a little bit on the TensorRent platform, it's an array of tiles, up to 64 tiles. So each tile has about five RISC processors for a total of about 350. I should mention, by the way, this is a collaboration with the University of Florida, SHREC, in collaboration with TensorRent. So let's take a look at how we actually deploy RISC-Bench on this test bed. So we start off with a workload, in this case, a matrix. We split that workload out into zones. So each zone is a combination of SRAM read, compute, SRAM write. Next, the program executes over a time bucket of n cycles. And then we're able to measure the instantaneous flops for that particular range of cycles. And then we can simply extract the sustained throughput and compute the SIT while the data is in SRAM. So that's the formula that I showed in the previous slide, where you can then do a summation of the various peaks over the time in which the data is in SRAM. I'm going to highlight a few results, actually 2 results in the interest of time. The first one is SIT per bucket. And so as you can see here, the throughput, the sustained throughput in this case, rises significantly up to 339 SIT ops. We call this SIT operations, synonymous to flops. As you can see, by T3, the throughput begins to significantly reduce, and that's mainly because of the synchronization overhead, with multiple threads being able to spin up over time. When we combine that with the cumulative SIT, you can see over time the trend shows that the later buckets contribute less effectively to the efficiency. So combined, both SIT per bucket and cumulative SIT really provide a pinpoint of where your orchestration begins to overshadow program execution. So kits are already showing up for RISC-Bench. It's not yet complete. We're looking for help from you all to help grow it. It is an open source benchmark. And the goal there is to expose orchestration inefficiency within this heterogeneous cores that I mentioned earlier as our motivation. We're welcoming community contribution, whether that is new hardware targets or novel memory architectures. In summary, synchronization and memory residency, not peak compute density, really define sustained throughput. And without tools like RISC-Bench, peak values really provide very little predictive value for actual workloads that are deployed. SIT is a platform-agnostic cross-platform tool for helping to address this challenge, and we showed 4 kernels in which we're putting out there for the community. We believe that the next wave of AI compute would not necessarily come from more GPUs, but rather how we orchestrate compute across these heterogeneous platforms, including for the use cases that we showed today, FlapZero and SkyZero. As I mentioned earlier, FlapZero CubeSat kits, dev kits, will be available next year. We're open to contribution. Here's the site. There's a little typo. It should say RISC and not RISC. So RISC-Bench, but you can scan the QR code also. More details are in the research paper coming up soon. If you want to learn more about NIOS V from Altera, there's another QR code there, and we're looking for more ecosystem support around expanding the EDA tool sets around this. A special acknowledgement to the various institutions shown here. We're open to meeting you, collaborating. We can be reached via these emails. Thanks for your time, and we'll take any questions.
Thank you for the presentation. I'm using anyway Altera tools for teaching for many years, Quartus, anyway, NIOS too fast, and anyway for many years. I noticed the Visual Design Studio is something new because we use Platform Designer. Is it supported in a standard edition of Quartus or not? Because we use Cyclone 5 devices because cheaper FPGA board.
It is not,
and one problem that we have, lots of new features comes to Quartus Pro, and that prevents us, we can only use for research. So is this supported or not?
No, it is only for the Pro tools.
Is there any plan to put it?
Not right now.
Okay, because in AMD or Xilinx, they have some consistent Vivado for everything. I think it would be good.
Yeah, for the standard version, we just have Platform Designer. So this is the next generation of Platform Designer in the Pro tools. But for standard, we're going to continue to support Platform Designer, at least for the near future.
Okay, another question, is there any new version of NIOS 5 near future will be available? Because NIOS 2 fast is better than NIOS 5G because of virtual memory and other things. So
yes, so we've been making improvements across versions. I think you're using standard, so the latest standard release is going to be available end of this year, I think, like Q4, December timeframe, I think, if it doesn't get delayed. But usually that's the timeframe. So everything that is available in Pro, all the latest features will be available in standard as well.
Thank you very much. Thank you.
Thanks, we're out of time.